In this lecture, we're going to talk about expected value, means, and standard deviation, and we'll be setting up a theoretical framework for a lot of what is going to be coming our way. We're going to talk now, recall our definition of a mean, and I'm going to come at it with kind of from an algebraic way. We have recall our mean of a population is the sum of all the values of that random variable divided by n. Okay. Now I can rewrite that algebraically as 1 over n times the sum, and then I can distribute that out. Okay, so I'm just at this point just playing with the algebra. Having distributed it out, I notice, okay, well, what this is, okay, is the probability that x is equal to x1 when we have equally likely outcomes, okay, and it's a probability that x is equal to x2 and x3 and so forth when we have equally likely outcomes. And then there's a special notation when we're adding up a bunch of things which have a similar form, the sigma notation. I start out, I let I equal 1, okay, and then I'll have I equal 2, and then I equal 3. The sigma out front stands for summation. I'm going to add up a bunch of things. Every time you see one of these sigma signs, say I'm going to have to add up a column of values. But it's just a notational shorthand to keep us from having to write out this every time. Okay. Now what I've done in switching this, I'm switching a notation, it enables me to talk about something when I have a different probability going on than just equally likely outcomes, and we'll talk about this in a bit. Okay, so let's define what the mean of a random variable is. Okay, let x be a random variable that has values x1 through x2 through xn. Define the mean of x to be mu sub x, which is the sum I equals 1 to n of the probability x equals x sub 1 times x sub 1. So we're just taking the particular value our random variable has times the probability that that value will occur in our experiment. Okay. The expected value of a random variable x is denoted by ex, and it is equal to the mean of the random variable. So it's just a handy notational device. Okay, a different word for the same thing. Okay, let's now switch to a random variable that does not have equally likely outcomes, and that's the binomial random variable. And calculate the expected value of that random variable x. Here we run through all of the values that x takes on. Remember, x counts successes, and so x will start out at 0 and it'll go up to n. And so the probability that x is equal to x times x, we start with x equals 0 times 0, x equals 1 times 1, x equals 2 times 2, etc. But recall, we do have a formula for the probability of x equal little x for the binomial. It's this right here. And so what we do, what happens here, we go through the algebra, and I'll just sort of kind of soft pedal it here. I'll take this x and I move it up out front up here. Now, when I multiply x times n choose x, if you want to, you can get your hands dirty and work this out. It works out to be n times n minus x, n minus 1 over x minus 1, excuse me, n times n minus 1 choose x minus 1. Okay. Now, what I do here, okay, I factor a p out of this, and it'll leave x minus 1. Okay. And what I do over here, I kind of reshuffle things around. I make the note that n minus x is equal to n minus 1 minus x minus 1. The minus minus 1 is a plus, and it'll cancel out. Just doing some algebra magic there. Okay. Having done that, I got my n and my p. And my n, neither my n or my p have an x in them. Okay, and so that means I can factor them both out front. Okay, this gives me what's left, the sum n equal 0 to n minus 1 of n minus 1 choose x minus 1 times p times 1 minus p to the n minus 1 minus x minus 1. This turns out to be what's called the binomial formula. Okay, and by the binomial formula, this sum is equal to this right here, and this right here, p plus 1 minus p, reduces to 1. Okay. And so this gives me n minus p. So done a whole lot of work, been a whole lot of algebra. Maybe a lot of it hasn't made sense to you. That would probably be about where you should be. But at the end of it, we've got that if we have x is a binomial random variable with n trials and a probability of p of success, then its mean is n times p. Okay, so a lot of times math teachers take it on the chin for, well, they just tell us the formula without telling it where it come from. Well, I just told you where this one came from. Okay, now what does it mean? That's what you really want to know. Well, let's take a look at the binomial random variable with 20 trials and a probability of 0.7 of success. And what I have done here, I have done a bar graph, a histogram of these, and laid them all out with the probabilities of the outcome be the height axis, and the number of outcomes being the horizontal axis. And you see a nice bell-shaped curve, okay, like we expect, okay, for binomial. Now, if I do my mean, I take 20 times my n, 20 times my p, 0.7, and this works out to 14. Well, 14 is right here, and look, for the binomial, that's right, that this highest bit right here for the binomial, your expected value, your mean, is right there in the middle of the bell. Okay, and most of your probability is concentrated very close to it, so you have a much higher probability of being, you know, within just a couple, one side or the other of the expected value than any place else. Okay, so much more likely to be there than 11 or below, or 17 or above. You can do the same calculation with n equal 15 and p equal to 0.4. Right? You do that, you get 6 right there in the middle, and most of our probability concentrated right there, because the things get very small for one side or the other. Okay. Okay. Now, let's look at variance. Okay. The variance of a random variable is the expected value of x minus mu x quantity squared. Right? And we denote that by sigma sub x quantity squared. We can first do a calculation that works for any random variable x at all. We square out the x minus mu sub x. We then use the properties of expected value to do a simplification of this. It turns out for any random variable at all, regardless of how it's distributed, we get that the variance is equal to the expected value of x squared minus the square of the mean. Okay. Now, let's work this out for the standard deviation. Right? Work this out to get the standard deviation of the binomial. Again, n with x's with n trials and p probability of success. After a lengthy calculation, and I suspect you will trust me now when I say lengthy, I mean lengthy. We get the expected value of x squared is equal to np squared times np times 1 minus p. And so we take that and subtract from it the square of the expected value. It gives us np times 1 minus p. And so we can summarize this by saying the standard deviation is the square root of np times 1 minus p. And put both of these formulas, these hard calculated formulas, together just to sit back and glow looking at them.